Who's going to talk about Stormtime, ion redistribution in mid-latitudes. So, Phil.
Thank you, Mr. Chairman. I'm very grateful to the Science Steering Committee at CEDAR for allowing me to talk to you a little bit about a subject that those of us who are at Haystack, and in fact those of us at Mid-Latitudes, have been thinking about for a while. But given that this is CEDAR and we're going for a new dimension in CEDAR, and there are these words on the board here which are more of a system-level perspective, I'm going to be talking about a particular phenomenon that we see using our incoherent scatter radar at mid-latitudes, but we're certainly not the only ones. And I'm going to try to step back and show you some of the interesting features we've seen about ion redistribution at storm times, but actually put it in a context that it's a real system, and one has to look at the system as a whole in order to really begin to advance one's understanding. Before I do that, I have to acknowledge my colleagues at Millstone Hill. I am extremely lucky to be working with such a fabulous set of scientists and programmers and many other things. Thank NSF's Upper Atmosphere Facilities for supporting the work that I'm going to be showing at Millstone Hill over decades now. Certainly CEDAR, we've been going through anniversaries. I came to my first CEDAR meeting as a student in 1989, and in fact, yesterday, when I came out of the plenary session, I almost turned to go back to the dorms to stay, because that's where I first started many years ago. So, I also want to thank NASA for some support of this work through the Living with the Star Targeted Research and Technology Program. Thanks to Google Earth, I don't want to try to write the program that they have, and I'll be showing you some of those pictures. And really, the entire space physics community, because this work involves CEDAR and GEM and the heliosphere eventually, and many, many other things. So, and I'm aware, by the way, there are students in the room, so I will attempt to point out terminology as I'm using it. Professor Mandillo preceded me, so I thought I would put this up in that the phenomena that I'm going to talk to you about, ionospheric redistribution at storm times, has certainly been viewed many times before, just with different tools and with somewhat a limited set of mesoscale observations. This is a work that Mandillo and Klobuchar published back in 1975. This is the old ATS geosynchronous measurement network. You'd look at a geosynchronous beacon, and you basically measure total electron content through differential Doppler along that line, and you would monitor things and see what happens. And in fact, during the dusk sector in the American sector, if those of you who have good eyesight can see the network here from Greenland all the way down to Kingston in Jamaica, and 4 of those stations at a sudden storm commencement right here would, in the dusk sector, see this very large total electron content enhancement. And at the time, there were not that many points sampling on this phenomenon, but it was certainly very significant, and many storm studies were started in the 70s, continued by the late, great Michael Buonsano, for example, and many things were learned about this. Now, of course, we have really nice visualization tools, and so here comes Google Earth. This, for example, is the November 20th, 2003 storm. And now we have sort of the prototypical example of the DASI concept, the Distributed Arrays of Scientific Instruments. This is the global GPS total electron content measurement network, created for geodesy, but very useful for ionospheric science. And there, and now imaged in 2 dimensions, is a total electron content plume. This is 0 to 60 total electron content units, very comparable to the thing I showed from Mandillo and Klobuchar. And there's this very nice plume of storm-enhanced density coming off mid-latitudes, going all the way up into, in fact, the entry to the cusp, going over the pole, although you can't see it in this view, and in fact exiting out into the night side sector. So, if one looks at that, in fact, in a polar plot view, which is from a paper that John Foster did in 2005, now you can see that same plume coming across, passing by Millstone. There's Sonderstrom, there's ISCAT, coming over the pole. There's the GPS to EC map. So now we basically have a system-level redistribution of plasma. Okay, so the question is, this is a very significant and repeatable visible feature for moderate to severe disturbances. By the way, we also had the DMSP satellite coming along. Those are those vectors here, and you can actually see the along track, cross-track velocity pattern here. We also have the super darn convection pattern. See, this is beginning to be a mesoscale sort of system-level study, which starts to reveal a lot of ion transport. So the question is, what are the drivers behind that? Well, there's concept that John Foster and Bill Burke named, at least, as the Sub-Auroral polarization stream, or the SAPS. Turns out you can find it, for example, in the Millstone Hill radar data. This is velocity, westward velocity or sunward velocity as a function of latitude here, invariant latitude. Here's the auroral oval at the time. And there's this sub-auroral feature, 2 to 5 degrees wide, located very close to the ionospheric trough. Okay, so now this is electron density again. And if you go look at the DMSP satellite, this is F-13 flying through the dusk sector, nicely. You can look at, this is the cross-track drift, and sure enough, there's that 2 to 5 degree wide electric velocity feature, which is in fact overlapping the edge of the trough and the storm-enhanced density plumes. And so now you start to think, this is what's transporting material through that dusk sector to the noontime cusp. Well, now again, I'm presenting a GPS to EC map. Now I've got 150 TECU here, and there's that plume coming along. If you take this and you map it out using Sigonenko mapping into the equatorial plane of the magnetosphere, so now I've broadened my view even further, you can even see a plume going out to several Earth radii, and now you're beginning to look at plasmaspheric structuring. So in fact, the ground-based signature of TEC has an analog out in the equatorial plane of the magnetosphere, and sure enough, you look in EUV with the image satellite, helium glowing at 304 angstroms, and you in fact see that plume extending off like this. And so now you can do very interesting coupled studies of how does this magnetosphere-ionosphere coupling affect what's going on in the ring current and the plasma sheet and other things in the magnetosphere. So see, we've extended our view even farther out. So we've been seeing this from Millstone for a while, and we have this very nice incoherent scatter radar, which for the students is a nice diagnostics, which eventually you get density and velocity and temperature and composition and many other things with certain assumptions. And we happen to be sitting up on top of a hill at Millstone Hill with a nice steerable antenna, which we've had since 1978. And one can make very wide field scans. This, in fact, is electron density back in 1980 when the solar cycle was really roaring. You can see the 10.7 meter flux here. And here you can see all of this structure. Here's the inner plasmasphere. There's the boundary where trough processes are going on. Here's where here's the high latitude processes. And if you take a look now, not at the electron density, but you look at, and so, like for example, Carpenter and Lemaire label this as the plasmasphere boundary layer, the place where interactions are occurring and where a lot of the interesting physics goes. So now if I plot, instead of line of sight ion velocity from 0 to 800 meters per second, that's blue to red, now you can see this sub-auroral polarization stream feature, but now we're looking at it sort of in 2 dimensions. This is a low elevation azimuth scan cut. And again, just to label it for the students, this is where that sub-auroral polarization stream is happening. So this is some of the structuring agent. So what I've done here is, you can also see it, for example, in DMSP. I mentioned that before. Here's the westward velocity. Here's the ion density. There's the storm-enhanced density. And where they overlap, we have sunward ion flux, a significant amount of sunward ion flux. So what we've done at Millstone is we actually have 10,000 or more scans if you go through our entire database from 1979 to 2001. And of those, some of them have this SAPS and enhanced flux feature. And so what we did was, John Foster and Hien Vo actually clicked every single one of these scans when they could find a SAPS and identify the mean latitude, invariant latitude at which the SAPS feature occurred. So we start to do statistics. So this is the statistical coverage as a function of magnetic local time, number here. And this, in fact, is if you organize it by the DST index, because these are the footprints of region 2 enhanced ring current, asymmetric dusk sector and night side ring current features. And sure enough, we have very good coverage for weak to moderate storms. You know, the superstorms are out here, but I'm going to concentrate there, which is more or less KP of 2 or greater. So the very interesting thing here is if you now sort this by, this is magnetic local time. This is now the sunward flux, product of density and velocity. And now I've binned it into 4 DST ranges, 0 to 50, and then getting increasingly more active. The thing that leaped out at us was there's not that much flux variation here as you turn up the knob and increase the strength of the ring current. Now, if you split that out into its electron density and ion velocity components, you see an interesting thing. As the ion velocity goes up, as the disturbance level gets larger, the electron density drops and they balance each other, such that the flux remains almost constant. It has a drop with magnetic local time, But at any one magnetic local time, there's not that much variation with activity. And what this goes back to, and we put this in a JGR that's now been submitted, is the Shunk effect of essentially as you drive this harder, you essentially get enhanced recombination. And back then, Shunk did a 50 millivolt per meter driving electric field, which is not that far off this red curve. And you see that there's a corresponding drop in density. But from a system point of view, I'm pointing on the board here, what you've got is a mechanism to almost regulate the amount of flux going sunwards from the dusk sector up toward noontime. And so in fact, if one just takes all DSTs combined now, the flux between 350 and 500 kilometers, the dashed lines represent the 1 standard deviation variability. Within a factor of 2 at any magnetic local time, I can tell you on average what the sunward flux is, and it's this, quote, magic number of 10 to the 14th, somewhere between 10 to the 13th and 10 to the 14th per meter squared per second. That's a flow of a few hundred meters per second times densities of a few times 10 to the 11th. Now, you can find something else very interesting about this. Just look at the velocity distribution in 2 magnetic local time sectors. So if I back up here for a moment, what I'm going to do is I'm going to look at this magnetic local time just before the terminator and this one just after it. What you notice is that for the time before the terminator, I've marked the average co-rotation velocity here. So for example, if all the flow were in a spike right here, essentially this is westward flow. We'd have a conclusion, I'll talk about it in a minute, but in fact, what we have here is that before the terminator, this flow on average is moving faster than co-rotation. What is that telling us? That telling us is that before sunset, this flow, just like we see in the SED plumes, is transporting material westward to the noon cusp. This is a mesoscale phenomenon that we are getting a nice snapshot with statistically. Now, if I go after the terminator, I get a distribution which is much more nicely peaked around co-rotation. So what is that telling me? In the inertial frame, in the Sun-Earth frame, this flow is fixed at a corresponding local time. So there's a fundamental difference in behavior if I'm before the terminator or after the terminator. There's some interesting geophysics in that. John and I have another paper that we need to essentially resubmit about some physical mechanisms why this would happen. But statistically, our measurements at mid-latitudes, I have to say in the American sector, because obviously we haven't moved our radar anytime in the near past, seem to bear this out. So you can do more, and I don't have time to present the results here, just to mention that we're actually doing this. When you have a scan like this, you can actually thread a line of constant magnetic latitude in here. The magnetic longitude, of course, varies, but if you assume that's constant, and for the students in the room, this is, for example, the expression for the Pedersen conductivity in the F region. Basically, we measure the electron density. We can pull some of these other things out of the models. And so I know the thread at which I've identified the SAPS midpoint. So I can start constructing integrated Pedersen conductivity in the F layer between 250 and 500 kilometers along this line, and then say 3 degrees equator to this line to look at what the conductance is doing. So one thing I want to mention about this before I go to my last slide here is that you'll notice something else about this. The terminator is happening here. I don't see a large signature of that in the flux. So again, I'm going back to that regulation. The conductivity is changing as we go into the night side. Okay, the E region is going away, but there's an interesting set of interbalanced processes here that combine to keep that flux nearly constant. And this has had an interesting discussion in the GEM and the TRNT communities, where they're also looking at sort of levels of characteristic flux going into the cusp. So the last point I wanted to make was something that happened. This was a study from 1999 to 2001, just to point out for the students that all hope is not lost. In fact, this does occur in the current solar cycle. My friends Mike and Craig and Mary at SRI have put up with me making little 3-day requests to just measure for 2 hours near the cusp on times which we think might be magnetically active. The point is, and we've been waiting for a while and trying to do this, is to catch one of these flows, which I know from Millstone Hill statistically are coming up like this. At this magnetic local time, for example, the flow would be about a few times 10 to the 14th in this channel, and to watch it go by on its way into the cusp. And sure enough, we caught one. at Poker Flat on May 31st of this year. This is the DPST-EC map. This is Mike Nichols' resolved vectors as a function of magnetic latitude, and there's this burst here. And the field got up to 50 millivolts per meter, or a kilometer per second. That's this little stripe here. Bill Wright and I are starting to need to put vectors into the KML here, but we're getting there. The point is that this cusp entry flux on its way into the cusp was about 3 e to the 14th per meter squared per second. That's almost precisely what statistically I would have predicted for the flow going by this magnetic local time. We've got a coupled system here. And so the geophysical implications are that there's a lot of transport coming into here. Now, how much of that flux actually ends up going and upwelling, for example, and performing some of the source of a lot of the cold ionospheric O+, which ends up mass loading the plasma sheet? How much of that goes across the cap and forms, for example, patches of ionization, tongues of ionization? That's still an active topic, all right? No, but of something of considerable interest to both the ionospheric community and also the magnetospheric community. So our thought is to take this and feed it into, for example, the RCM model, those coupled models, to try to put some not only flux but conductance sort of realistic conditions in here and see if we can look at the balance of transport here. But remember, we're looking at a whole system. And again, for the students and those people doing future research, just to mention, it's a system-level response. It requires system-level observations in science. But look at what we have available. I've just marked on this map. We have Pfizer. We have Riser north and south, one constructed, one under the construction phase. We have Sonderstrom. We have Millstone. We have a DMSP coming through every dusk at 6 and 9 p.m., more than one DMSP, right through the period in the American longitude sector where these plumes are really active. And of course, we have Arecibo and Jicamarca down here looking at the very inner plasmasphere, looking at electric fields and drifts near the equator. We have Superdarn sitting there. In fact, it sees this very flow that I showed you just a moment ago from Pfizer. There's this nice flow. You can put this into a picture. And the point is, it's a coupled picture. But as you saw much earlier in my talk, it has implications not only for the ionospheric flow, but the magnetospheric flow and what happens in the plasma sheet and many other kinds of processes. So for those of you who are just starting out in this field, it's a really exciting time. There's lots of really fabulous measurements coming up. And the models, which I haven't even touched on here, are getting extremely sophisticated. And as Dr. Robles so convincingly showed us, are coupling now. So we are now putting everything together. There's plenty of interesting physics to look at in here. This is just my summary, and I am very grateful for your attention. And watch this space for future developments.